Welcome you all to Principles of Organic Synthesis. Presently we study nucleophilic aromatic substitution reaction. In this topic, so far we had 2 lectures in which we studied the addition and elimination reaction, elimination addition reaction, reactions of diazonium salts, and the reactions that involve radical ion intermediates. We also have seen some examples for the CH functionalization reactions. In continuation with these reactions, today we will try to focus on some of the aromatic nucleophilic substitution reactions. As we have discussed in the last class, if the aromatic ring has electron withdrawing group, the nucleophile can undergo reaction para or ortho position with respect to the electron withdrawing substituent. And if you have the leaving group, the reaction can be facilitated. We have seen some examples. If you look at here, and this intermediate, you have the aromatic ring where you have the electron withdrawing group. So when the nucleophile undergoes addition reaction, you will have the carbon ion intermediate. Once if you have the carbon ion intermediate which can lose hydrated ion, which is high energy species, and you will be able to get the substitution product. What you do here, addition followed by elimination, you get the nucleophilic substitution product. As we have seen earlier, the nucleophile can substitute ortho or para position with respect to the electron withdrawing group. Initial addition for the nucleophile to the ring, the addition reaction, then you form the carbon ion intermediate. Subsequently, it loses hydrated ion to give the nucleophilic substitution product. Here an example shown. Let us take the nitrobenzene. It is a strong electron withdrawing group. It can readily undergo reaction with this nucleophile. So you can see here, nitrobenzene can react with the reactive nucleophile such as amide. So here you have the potassium amide. In this case, the reaction takes place para position with respect to the nitro group. You will have the intermediate which can lose the hydrated ion, and you will be able to get the substituted compound. Here another example shown. If you look at this example, this 1,3-dinitrobenzene, this is now more reactive, this aromatic ring, comparing to the previous system, because you have 2 strong electron withdrawing group. Now the reaction takes place in this case at this carbon, because this is ortho to this as well as ortho to this functional group. Therefore, the cyanation takes place in this carbon as shown here. Addition to this, you will be able to have this intermediate. This carbon ion can be stabilized by the electron withdrawing group. Therefore, the reaction takes place in this carbon ortho position with respect to the nitro group. You can have this which can lose a hydrated ion. You will be able to get the substituted compound. So here another example shown. In this case, this also nitrobenzene, and if you take this substrate and this hydrogen is acidic enough, when you have the base, it can deprotonate. You can generate the carbon ion which can act as a nucleophile, in this case which undergoes reaction ortho position, and you will be able to get this product. This substrate with both a mixture of ortho as well as para substitution reaction has been observed. As you can see here, you make a CC bond formation. Here also shown another example where, as just we have seen here, the substitution reaction can take place. The base can deprotonate, you generate the carbon ion which can act as a nucleophile which can undergo addition followed by elimination reaction. You will be able to make the substituted thiophene derivatives. The mechanism for this reaction shown here, when you take the nitrobenzene and the presence of base, you can deprotonate, you generate the carbon ion which acts as a nucleophile which can undergo addition reaction. If it takes place the ortho position, you will have this intermediate. Since you carry out the reaction with the base and it can lose proton, then you lose HCl in this case, and the base can deprotonate, and this can also leave, then you will be able to have this intermediate. Once you form, this can aromatize to give this 2-alkyl nitrobenzene as a product. And similarly, you can also undergo in the para position, then you will be able to get the para substituted nitrobenzene as the product. So, now let us look at some of the name reaction, which also in principle nucleophilic substitution reaction. Now, let us take the pyridine, and if you compare with the benzene, we have seen several examples for the nucleophilic substitution to benzene. It happens when you have the strong electron withdrawing group, the reaction takes place, and if you see the energy level of nucleophile, and the LUMO of benzene, and this is the so the reaction takes place between this LUMO, the lowest unoccupied molecular orbital of benzene with this highest occupied molecular orbital nucleophile. The reaction takes place here, and if you compare the energy level of pyridine and is below and is very close to the nucleophile. Therefore, this is because you have the strong electron withdrawing group, the nitrogen atom in this ring. Therefore, the energy level LUMO of the pyridine is lower comparing to benzene ring. Therefore, this substrate can undergo nucleophilic substitution more favorably comparing to benzene ring. Now, let us look at the amination of 2-pyridine. If you have sodamide in liquid ammonia, you can generate this amide which can act as a nucleophile which can undergo reaction in the pyridine, and in this way you will be able to make 2-aminopyridine as a product, which is known as Chichibabin reaction. So, pyridine and other heterocyclic compounds can be aminated using alkali metal amides. So, this very strong nucleophile, when you have this one and liquid ammonia and it can undergo reaction with the pyridine, you will be able to make 2-aminopyridine as the product. The reaction pathway is shown here. So, addition to this double bond, you will be able to generate this intermediate which can lose hydride. So, you will be able to get the 2-aminopyridine. Since you lose sodium hydride, this hydride can act as a base, it can deprotonate, and you will have this intermediate NH minus and Na plus. You will have this one. Once if you have this one, when you do the aqueous workup, you will be able to get 2-aminopyridine as a product. This is a reaction pathway of this Chichibabin reaction. What happens here? First, addition of amide ion takes place. You get this intermediate which loses hydride ion. Elimination of the hydride ion can give this 2-aminopyridine reaction. If you look at overall, this also involves addition followed by elimination reaction. Overall, you get the substitution product. Here some more examples are shown, not only pyridine, and the pyridine, if you look at here, the reaction takes place this position, and similarly here also can take place, 4th position also. Similarly, if when you take the here quinoline, this also can undergo reaction this position or this position. You can see here when you take, as just we have seen, sodamide and liquid ammonia, you get the addition product. Once you have this one, this can lose hydride ion, as just we have seen. So, the 2-aminoquinoline you will get it, and where you will generate So once we have this one, and here they have further reacted with HNO2 water, you will be able to get so this will be converted into hydroxy derivative, which can exist in the form of this carbonyl compound. Similarly, if you take the 2-aminopyridine, this also when you react with sodium nitrite and HCl water, then you will be able to transform hydroxy compound, which you can exist as 2-pyridinone. And now another example, let us look at here. This also, as just we have seen, when you take the potassium amide in a liquid ammonia, it can undergo reaction. You can see here, you can get this amine derivative. So far we have seen if you have pyridine and analogues which can be readily reacted with alkali amides to give the substitution product. First the addition followed by elimination. The addition takes place, which eliminates hydride ion to give this substituted compound. The next example is, instead of sodamide, if you have alkyl lithium, this also can undergo reaction. So this is known as Ziegler alkylation. For example, the reaction of pyridine with N-beta lithium shown here, when you treat this one, and you will be able to get 2-alkyl pyridine as a product. And here what happens, as we have, if you remember the case of ortholithiation, suppose if you remember here, let us take anisole, and when you react with N-beta lithium, here this acts as a base, it is a deprotonate, then you will be able to form plus butane. Here it acts as a base, but here look at here, as we have seen, the lone pair of nitrogen make chelation with your this electropositive element lithium can make chelation. You will be able to have this intermediate. Once if you have this one, here this acts as a nucleophile, it undergoes addition, then you will be able to have this addition product. Once if you have this intermediate, it can, as you can see here, it can convert into this 2-alkyl pyridine, where you generate the lithium hydride as a product. See, in this way, if you have the alkyl lithium, we can here also look at first addition followed by elimination takes place, you get the substituted compound 2-alkyl pyridine as a product. Now let us look at the reaction of nitrobenzene with cyanide ion in ethanol and heat. This is known as von Richter rearrangement. When an aromatic nitro compound is treated with potassium cyanide, the nitro group is displaced and carboxyl group enters the cyan substitution. So here what happens, this has been this is gone, and instead of that you are adding a carboxyl functional group, this carbon. So you get the cyan substitution. Now let us look at the mechanism of this reaction. So this reaction is very important for the mechanistic aspect. However, when you go for synthetic utilities, they have limitations because the yields are very less, and less than 50%, always it gives mixture of compounds. Therefore, this reaction is not widely used for the preparation of the compound. However, for the mechanistic aspect, it's very interesting reaction. Now let us look at the nitrobenzene. As we have seen this, now it can act as a nucleophile which will undergo addition to the aromatic ring at the ortho position. So you have this intermediate. Once if you have this one, so deprotonation of this can give this intermediate where you have the HCN. So this now this lone pair can take this proton, then you will be able to have, so you lose cyanide ion, you will have this intermediate, intramolecular cyclization, and you will have this intermediate. Once you have this one, now this can open up and you will have this nitroso derivative which can undergo intramolecular cyclization, and since you have the to give this derivative which can now, since it can take proton, so you can have this one. Once if you have this one, now you have the base can deprotonate this one, then you will be able to lose water molecule. You will have this intermediate. Once we have this one, the hydroxide ion can now undergo addition reaction. You will be able to have this intermediate which can now lose nitrogen molecule. You will have the carbon ion intermediate. Once you have the carboxylic acid derivative, when we do the workup, you will be able to get this RL carboxylic acid product. What happens here? You lose here this functional group and you introduce another functional group at the ortho position with respect to the nitro group. You introduce a carboxylic acid. So this reaction is interesting, as I mentioned, with respect to mechanistic aspect. Now let us see some examples. Here an example shown, and here the reaction of the nitro derivative is shown here. When you react with this one potassium cyanide in the ethanol solvent water medium, and you will be able to introduce carboxylic acid group here. So similarly here the reaction of this nitro derivative, you have the bromo substituent ortho as well as meta position. When you carry out the reaction, and the reaction can take place as this carbon atom. So the potassium cyanide can undergo addition here. So you will be able to get the carboxylic acid derivative. So this way this reaction has been investigated around 1950, and this now the mechanism has been explored. And as you can see here, so although this reaction is not considerably explored for the synthetic utilities, however, this is a very interesting reaction with respect to the mechanistic aspects of nucleophilic substitution reaction. Now let us look at the Smiles rearrangement, and here when you have this kind of substrate, X should be a functional group, can be sulfone or ether, which is capable of leaving from the aromatic system when you have the anion carbon ion intermediate. So this functional group sulfone, ether, they are capable of dislodging from the aromatic system when it is nucleophilic nature, when you have the carbon ion intermediate. So this Y should be a strong nucleophile, like it can be O minus or carboxylate. When you have a strong nucleophile and which can make reaction, which can undergo addition reaction, at the same, when this can leave from the aromatic ring, what you do here, the Y goes here and X comes out. This is known as Smiles rearrangement. An example shown here. When you take this substrate, so in the presence of base, you can deprotonate. So you see the phenoxide anion which can now undergo addition reaction, and this comes out, then you will be able to get this compound. This is known as a Smiles rearrangement. The mechanism of this reaction shown here, in the presence of base, and you deprotonate this proton, then you will be able to have this intermediate which can undergo intramolecular addition reaction. And you will be able to have this intermediate. Once we have this one now, so you will have this intermediate. Once you have this one, now this can leave the, so it can, when you have the carbon ion which can leave, then you will be able to have this compound. Basically what happens here, this undergoes addition reaction, then this leaves from the aromatic ring, you will be able to get this substitution compound. Here, as you can see, the spirocyclic anion is intermediate in this reaction. Once you form this one, then now it can leave. This is a good leaving group comparing to this oxygen, therefore you will be able to get this substitution compound. Some more examples are shown for the Smiles rearrangement. Let us look at this amide. So this amide in the presence of base can deprotonate, then you will be able to have once you form this one, now this can undergo addition reaction, as you can see here, then you will be able to so this can now so you will be able to have so this, when you do the hydrolysis, base hydrolysis, so you will lose this portion, then you will be able to get diarylamine as the product. And similarly in this case, when you react this heterocyclic compound in the presence of base, and as we can see, just we have seen, and you have use the sodium hydride, it can deprotonate. You lose hydrogen gas, so you will have have this intermediate which can, as just we have seen, it can undergo addition reaction. You have this intermediate. Once we have this one, so this can, now it can convert into so when you do the hydrolysis, as just we have seen, when you have, for example, this, when you do the hydrolysis with base, and you can lose this functional group, you can convert into this amino derivative. So these very useful reactions, you can try to, if you have the leaving group like oxygen or sulfone, and you can react with a strong nucleophile, and you can dislodge. In this way you can get the substitution product. The next one is the reaction of aryl hydroxylamine with the presence of acid, which can rearrange. You get the 4-aminophenol as the product, you can see here, and this is very straightforward reaction. Suppose if you have the, for example, this phenyl hydroxylamine, when you treat with the acid and you will protonate, once you protonate, then you lose water molecule and you will be able to have this intermediate, which can, you can write the resonance structure when you so you will be able to have this carbocation. Once this can, you can try to write like this. Once we have this one, this now the water can attack, and you will be able to have this intermediate which can lose a proton, and then in this way you will get the 4-aminophenol as the product. So if you have the, so phenyl hydroxylamine, you can, when you react with the acid, you can make the phenol derivatives. Now let us look at some examples. Now let us look at this one. So this compound, when you react with acid, as just we have seen, and you can make, you can try to introduce the hydroxy group at the para position, you can rearrange, and which has been further oxidized to benzoquinone derivative, as you can see here. And so as just we have seen, protonation of this compound so you will have this cation. Once we have this one, now this can, you can try to write, draw the resonance structure. Now this water molecule so which can lose proton. So you get this 4-aminophenol derivative as the product. This another example shown here, as we have seen this hydroxylamine can be just we have seen the presence of acid can be converted into these aminophenol derivatives as a product. Here another example shown, and if you have the for example naphthol or naphthalamine, so which can be readily converted into, for example, if you have the beta naphthol, when you react with the sodium sulfite and ammonia, it can be readily converted into this naphthalamine. Similarly, if you have the naphthalamine as the product, when you react with the aqueous sodium sulfite and you can potassium hydroxide, you can convert into beta naphthol. So here example, naphthol can reacts with aqueous sodium sulfite to give aromatic amines. Similarly, if you have the naphthalamine which also can react with the aqueous sodium sulfite in the presence of potassium hydroxide, it can also convert into beta naphthol as the product. Let us see the mechanism of this transformation. You can see here the beta naphthol when you in the presence of acid, so it can take this product, you will be able to form this intermediate. Once you form this one, now you have the sodium sulfite which can undergo reaction as shown here, and then you will be able to addition reaction, and you will be able to have this intermediate. Once if you have this one, this can convert into keto form by isomerization. Once if you have this one, now this ammonia can undergo addition reaction with this carbonyl group, and you will be able to have this intermediate. Once if you have this one, by proton transfer you can form this species. Once you form this one, now this can lose water molecule, then you will be able to have, so this imine derivative, once you form this one, then this can convert into amine. At the same time it can also lose sulfite ion, you will be able to get the naphthalamine derivative. Here the crucial step, suppose if you have this is a reversible reaction. In this place, if you have for example OH minus, it can react and you will be able to get the hydroxy compound. But in this case, since you do not have that one, you have the so ammonia as nucleophile which can undergo addition reaction, and once form the imine intermediate which can now convert into the amine derivative. It is a reversible reaction, and just as I mentioned, instead of if you use the beta naphthol, you get this amine. On the other hand, you can also have NH2 here. If you use potassium hydroxide, you will be able to get, for example, if you have so beta naphthol, you can use same condition, sodium sulfite, aqueous sodium sulfite. Suppose if you use ammonia, you get this compound. On the other hand, if you have this is a starting material, so you can use sodium sulfite, so aqueous sodium sulfite, and basic conditions you will be able to get so beta naphthol as the product. You can try to draw the mechanism similar way, then you will be able to understand. Now let us look at some examples for the transformation. Now is given here, when you take this binol, when you react with ammonium sulfite, so just we have seen the sodium sulfite, in the place of sodium sulfite you can also use ammonium sulfite, ammonia, and that means you can try to replace the OH group into amino group, as just we have seen. You have to carry out the reaction at a high temperature for longer reaction time. You will be able to get this amino derivative. And similarly, in place of if you use this beta-naphthol using ammonium sulfite, ammonia, then you can get the corresponding amine as the product. This reaction has been carried out at microwave conditions. So, when you do the reaction under conventional heating, it takes longer time, as you can see here, and now you can also use microwave irradiation technology. Therefore, you can enhance the reactivity of the substrate, some of the reactions. So, here for example, the reaction of the beta-naphthol has been shown using the microwave conditions. The reaction can be completed in 30 minutes to give the amine derivative. Here another example shown, and this reaction involves sodium sulfite and ethanol and water medium. So, the amine has been replaced by hydroxy group. So, as we have seen earlier, then you can try to react. As we have seen, then you can try to draw the mechanism, and you will be able to understand the formation of this compound. Here the replacement of OH group with the amino group is shown. Here the ammonia is used as nucleophile using sodium sulfite and aqueous sodium sulfite. The ammonia, you can make this amine derivative. These are some of the recent examples. As you can see here, this method provides an effective synthetic route. If you have the amino group, you can convert into the phenol derivative. On the other hand, if you have the hydroxy group, you can convert into the amino group. So far we have seen some of the examples for the aromatic nucleophile substitution reaction. First, we have seen the reaction of pyridine with the soda amide or potassium amide, which is known as Chichibabin reaction. You can undergo addition reaction at 2 or 4th position of the pyridine under strong basic conditions to give the addition product, which involves addition followed by elimination reaction. You can get the 2 amino or 4 amino pyridine as the product. Then we have seen the rearrangement reaction. For example, if you have the nitrobenzene, you can try to react with cyanide ion. You can try to introduce carboxylic acid group at the ortho position, where you lose the nitro group. In this way, we have seen some examples. This reaction, as just I mentioned, is synthetically less useful. However, is a very interesting reaction with respect to the mechanistic aspects. Then we have seen some of the example, for example, rearrangement, smile rearrangement, and if you have the good leaving group, and you can try to replace, and you can get the substitution compound. Then we have seen the rearrangement of aryl hydroxylamine. If you have the acidic conditions, you can convert into 4 amino phenol derivatives. Then we have seen the rearrangement of beta-naphthol in the presence of aqueous sodium sulfite and ammonia to give the corresponding amine derivative. This reaction is reversible, and if you have the corresponding amine derivative, that also converted into beta-naphthol, if you using same aqueous sodium sulfite in the presence of potassium hydroxide. We have seen some applications of this important transformation. Now let us look at some cross coupling reactions. The first one is Heck reaction. If you remember the lecture where we studied Nikashi coupling, for example, if you have the aryl halide and organo-zinc reagent, you can try to couple them via using palladium nickel based catalytic system for the CC bond formation. So, similarly, here also if you have the aryl halide, here example which can be reacted with alkene, you make a carbon-carbon bond formation, which is known as Heck reaction. For an example shown here, let us take this aryl halide. This in the presence of palladium acetate and phosphine ligand and silver carbonate, it undergoes addition reaction. You get this palladium intermediate. Once we have this one which undergoes further reaction, and you will be able to get this tricyclic system where you make a 2 carbon-carbon bond. This is known as Heck reaction, and Nikashi Heck. So, this in 2010 the Nikashi coupling, Heck reaction and Suzuki coupling got Nobel Prize. So, this is one of the powerful reaction to make a carbon-carbon bond, and for example, using this method and this anti-inflammatory drug naproxen has been synthesized using this reaction. So now let me try to explain the mechanism of this transformation. So this reaction, the palladium 2 is reduced to palladium 0. So since you have the possible ligand, the palladium C is converted into the palladium 0, the reaction medium. Once you form this one, now this can undergo reaction. Now let us take this an example, then it will be easier for you. Now let us take bromobenzene as the substrate. When you react with, for example, this alkene, and which can undergo reaction, you will be able to get this as the product in the presence of palladium acetate and phosphine ligand and base under nitrogen atmosphere. This standard condition, when you take this aryl halide with alkene and the presence of palladium acetate and phosphine ligand and base, and you will be able to make a CC bond, and where the palladium 2 is reduced to palladium 0. Once if we have this one which can undergo oxidative addition with your aryl halide, let me write like this, and it can undergo oxidative addition, then you will be able to have a palladium 2 intermediate Once you form this one, now this can react with your alkene So once if we have this one, now this can insertion reaction, this is oxidative addition. So then once then it bicomplex formation takes place with this palladium, chelation of this, you will have this intermediate which can undergo insertion reaction. Now this can come here and this can go here, then you will be able to have insertion reaction. So you have the AR here and you have the, so when you have the palladium and this one syn, the beta hydride elimination takes place. So it can go here, this can come here, then you will be able to have palladium Br plus your alkene so this one, this can now can undergo reductive elimination. HBr, you have the base in the reaction medium which can react with HBr, then you will get back. What happens here? First, the palladium 0 can undergo oxidative addition with your aryl halide. You have the palladium 2 species. Once if you have this one, this can react with your alkene, and you will make the first bicomplex. Then insertion takes place. Once you form this one, you will be able to form this intermediate. If you have this hydride and the palladium syn, since a carbon-carbon single bond, it can rotate, and so once you have the syn, it can undergo beta hydride elimination. Then you will be able to have this intermediate, and you lose the alkene, and this can undergo reductive elimination to complete the catalytic cycle, and whatever HBr that you generate, that can be reacted with the base, and the reaction so the Heck reaction is one of the powerful reaction to make a carbon-carbon bond. This common reaction condition shown here, and for example, this has been used to construct this tricyclic compound where you form a 2 carbon-carbon bond. It is very difficult to form by conventional methods. So the cross coupling reaction provides a powerful synthetic rule if you want to make a carbon-carbon bond, and this is one of the effective synthetic routes to make the coupling of alkene with aryl halide, and in this way, for example, this has been used to make this drug. This is we use as an anti-inflammatory drug. This method is used to industrially to produce this compound. The next example is Suzuki reaction, where if you try to remember the Heck reaction, where the reaction of aryl halide with alkene is shown, the presence of palladium acetate, you make this styrene derivative, but here if you look at here also aryl halide, you can use it, aryl or vinyl triflate. For example, when you take this vinyl triflate, it can be readily reacted with boronic acid. In the presence of palladium acetate, phosphine ligand and base, you can get this CC coupled product. So in this way, you can try to introduce vinyl functionality in the aromatic ring. And this example, for example, this diiodoindole derivative has been coupled with the boronic acid. In this way, you can introduce 2 aryl rings in this indole moiety. The reaction condition shown here. Here also they use palladium acetate and phosphine ligand and base. And if you remember the Heck reaction, usually they use their DMF. Here you can use THF for acetone or solvent. Now let us see the mechanism of this reaction. As just we have seen, here also the palladium 0 is involved, and the palladium 2 is reduced to palladium 0 in the reaction medium. Once if we have this one, now as just we have seen, it can undergo oxidative addition, the aryl halide. Let me write as aryl bromide, the oxidative addition can this palladium 2 intermediate. Once you form this one, this can react so you will be able to have this intermediate. Once if you have this one, now you have the boronic acid. So when you react with the base, so when you react with sodium hydroxide, you will form this salt. So this salt, when you add, this salt when you add here, you will be able to form So, let me write AR prime. So, this can give the product by reductive elimination. So, you make a biaryl system, an example shown here. Suppose if you have the aryl bromide, aryl boronic acid, you can couple by a CC coupling reaction using palladium acetate and phospholigand in the presence of base like sodium hydroxide or sodium methoxide or potassium carbonate. You can this is the mechanism shown here, and the palladium 2 is reduced to palladium 0. Once you form this one, this can undergo oxidative addition, and which can undergo reaction now as is shown here. When you react with this, you can form this intermediate. Once you have this one, this can react with this salt. So, you can form this intermediate palladium 2, which can give the product by reductive elimination. So, this is very crucial, this reaction formation of this 8 complex. So, another one more reaction very for the CC bond formation, and this is known as Steno-Koshira coupling reaction. So, in this reaction, if you have aryl halide, so alkyne, and you can try to couple solvent, you will be able to get this as the product. So, here if what happens this when you take the tetrahydrocyclic potassium palladium and copper on iodide in diisopropylamine and THF solvent under nitrogen atmosphere, the copper on iodide can react with this alkyne. You will be able to form this copper alkyne derivative. Once you form this one, which can, as we have seen, this also can undergo oxidative addition with this one, as just we have seen, and you will be able to have so this intermediate, which can now undergo reaction with this copper alkyne derivative via transmetallation. So, this can give the product by reductive elimination. So, if you have the aryl halide, that also you can try to couple with the alkyne. If you have the terminal alkyne using the palladium acetate, copper iodide and diisopropylamine THF solvent under a nitrogen atmosphere, you can try to couple. You can make the substituted alkyne, and these are the very common and powerful reactions if you want to couple aryl halide. And you can the first one we have seen the Keck reaction. If you have the aryl halide, you can couple with alkene and you can make the styrene derivatives. The second example we have seen, if you have the aryl halide, you can couple with the aryl boronic acid. In this way you will be able to make a biaryl system. And the third example we have seen, and here this is known as Steno-Koshira coupling reaction. And if you have the aryl halide, if you have the alkyne, you can try to couple. In this way you can make the substituted alkyne as the derivative. In summary, in this class we have seen Chichibabin reaction, where if you have the pyridine derivative which can be readily reacted with soda amide, and you can undergo addition followed by elimination reaction. In this way, for example, if you have the pyridine, you can make 2-aminopyridine as the product. If you have the quinoline, you can also try to react similar way. You can get the aminoquinoline derivatives. You can also try to react with isoquinoline. You can get similarly, the amination will take place at the C1 position. You will get the corresponding aminoquinoline derivatives. Then we have seen the von Richter rearrangement, where if you have the nitro compounds, you can try to react with the cyano derivatives. You can introduce carboxylic acid, and where you lose the nitro group. This reaction mechanistically is very interesting one, although it gives a mixture of compounds. It is not used widely in synthetic utilities. However, with respect to mechanistic aspect, it is a very useful reaction. Then we have seen the Smiles rearrangement. If you have the good leaving group like sulfone, and if you have the good nucleophile, and in the presence of base, it can undergo substitution reaction. Then we have seen the Bamberger rearrangement, following that the Bucherer reaction. Then we have seen the CC cross coupling reaction. We have seen in this class 2 examples. The first one, we have seen the Heck coupling reaction. Suppose if we have the aryl halide, and if you have the alkene, you can try to react in the presence of palladium acetate and phosphine ligand and base, and you will be able to make the styrene derivatives, which is very useful reaction, which has been widely used in medicinal chemistry to construct drugs. We have seen one example. For example, naproxen has been synthesized using this reaction. Then we have seen Susi coupling reaction. For example, if you have the aryl halide and you can try to couple with boronic acid in the presence of palladium acetate and phosphine ligand and base. So, in this you form the 8 complex, which is crucial to push forward the reaction. Then we have seen the coupling of aryl halide with the terminal alkyne. If you have this one, this also you can carry out the reaction. For example, if you have the tetrahedral triphenyl passing palladium, copper 1 iodide, and diisopropylamine THF solvent, you can try to also couple. In this way, you will be able to form the substituted alkyne derivatives. Here you can make the styrene derivatives using this method, Susi coupling reaction. You can make the biaryl system. So, these all reactions are a very powerful reaction for the carbon-carbon bond formation. If you look at in all the case, use aryl halide as the substrate. So, if you have the aryl halide, it can be readily coupled with alkyne, terminal alkyne or boronic acid or alkene to give the corresponding CC coupled product. For the discovery, Professor Suzuki, Professor Keck and Professor Nigeshi received a Nobel Prize in 2010 for the CC cross coupling reaction. And if you remember, we have discussed about the Nigeshi coupling reaction. If you have the organo-zinc reagent, which can be readily coupled with aryl halide in the presence of palladium or nickel catalyst, and this also one of the powerful reaction for the carbon-carbon bond formation. So, with this we conclude this lecture. Thank you very much.